So good morning. So today we go, as you now gradually start to see, is this course. Of course, we treat various aspects of what we call quantitative risk management in a sort of a very fast mode. I still remember I stood in one of these rooms, it might have been this room, about 20 years ago, giving a full course, a summer school, on extreme value theory. Now, I'm giving, let's say, a 1-hour lecture on extreme value theory. And of course, you know that we wrote a book with Kluppelberg and Mikos in 1997 on modeling extreme events for insurance and finance. And again, in the spirit of this course, we want to explain to you tools and techniques which we think are relevant. Some of you may be more in contact with some questions on aggregation, dependence. Others may more be using tools from, let's say, time series analysis. Others may be using aspects from extremes. Extremes, I think, are extremely important in risk management, because risk management is about understanding extremes. So I think any course, I often say, the little section in the book, which I think is extremely nice section, the Introduction to Extreme Value Theory, for me is Finance 101. You know, the American system. This is every student all over the world in econometrics or finance should know this. Because too often we have heard statements like, well, that's a one in the lifetime of the universe events, or the world is non-Gaussian, and so these are all blah, blah, blah statements. So this section is about, there is a theory out there which allows you to talk about extremes, allows you to understand it. It's not going to make your life easier. On the contrary, it make your life more difficult, because the main pedagogical setup of this particular chapter of this theory is to warn you asking extreme questions. If you say, I want to measure operational risk, for those who know it, a 1 in 1,000 year event, a value at risk at 99.9 level, 1 year, then it's essentially extreme value theory that can tell you, forget about it. If you give me high quality data, I can do something on basis of the data available. This is a nonsensical question, although we have written various papers on it. But extreme value theory is there not to say, oh, now I've got a magical theory that allows me to answer these questions. And believe me, in the beginning, where we were introducing this field into finance in the 90s, people thought, now we have the tools available for finally answering these extreme questions of these very, very high return periods. It's the contrary. Extreme value theory allows you to have sufficient data, but it tells you very carefully, this is the end of the line. Okay? That's, I think, the main message I want to give to you. And so we give a very short introduction to extreme value theory. First of all, and I often, when I teach my students, I say, I've got models in my right pocket, I've got models in my left pocket. In my right pocket are all the models that have to do with sums. So I look at IID random variables, and these independence, identically distributed condition, believe me, we can generalize it. That's not the issue. Let's just, again, as I said yesterday, let's first walk, and then we can run. So if I have IID random variables, and you're interested in the sum or the average, then we all know if you want to calculate the distribution, that's very difficult. You can basically not do it, except for very few examples, but you can approximate it well. You can approximate it by the Gaussian, if you have finite variance. If you don't have finite variance, you get the so-called stable distributions. So there's a well-known class of models that approximate statements on sums. This is an incredibly fantastic theorem. A main issue I want to press here is this approximation of questions on averages of some average behavior in markets is governed by the Gaussian distribution in continuous time, is governed by Brownian motion, logarithmic Brownian motion, whatever you want to think about. This holds, in the case of this theorem, the central limit theorem, for every distribution function of my data. You only need finite variance. And I want to press that for every. However your data is distributed, your model there, if you look at sums, skew, discrete, for those who know singular, this works. That's total magic. All right, so do you know this world? What we do is we sort of normalize by the mean and standardize by the standard deviation, and it's it. Magical result. Is there something like that for Maxima? Because I said, now I put the normal distribution, stable distributions in my right pocket, and if I have a question about sums, this is my model. And this is used every day, every millisecond, all over the world, in every field of science. Now I've got questions about the largest event, records. The Olympics are going on now. What's the probability of a record being broken, this and this and that? So, sports records. Can I use the Gaussian distribution? Well, you shouldn't. You're not talking about average behavior. The Olympics is about the best behavior. So you need different models. So rather than looking at the sum, I now look at the maximum. I'd give as an example the maximum. It can be, let's say, the second largest, the fifth largest, records, but all. Just let's look at the canonical example, the maximum. And again, is there a standard model out there? Well, I cannot guess it, and if the first time you hear the story, I'm sure you cannot guess the solution, because it's a non-trivial solution, but in my left pocket, I need other models. How do I find them? I mimic the central limit theorem. I say, okay, perhaps if I normalize it, like the mean and the standard deviation in the central limit theorem, perhaps I can find some limit, just like in the central limit theorem. And this h, if I can find it, this I put in my left pocket. That's an asymptotic model for talking about extremes. It's identical questions. Now here I mention one other result here. I will call xf the upper endpoint of a distribution. It's clearly, if I talk about records or extremes in uniform 0-1 distributions, random numbers, then the upper endpoint is 1. The largest observation is 1. If I talk about the exponential, the upper endpoint is infinity. So xf, I call the upper endpoint. Clearly, the upper endpoint plays an important role, finite or infinite. And clearly, if I sample and sample and sample, and I look at the largest observation, of course it will keep on moving to the right. And eventually it will converge, almost surely, for the mathematicians, to the right endpoint. It's like the law of large numbers, but for maxima. Doesn't tell us very much. We really have to find this here. Is there, because we're interested in risk measures and return periods, so we're interested in the distribution of the maximum, which of course I can trivially write down because it's an IID sequence, so the probability that the maximum is less than x is the n power of the marginal. So it's trivial. But of course I don't know the marginal distribution, so I need an asymptotic distribution. All right? This is just a pedagogical statement, is that there's good and bad news about extreme value theory. The good news is the distribution of the maximum itself, I can write down, is the n power of the marginal. That's the last good news you get from me. All the other news is bad. Although I can solve the problem, but it's a very difficult world to work in, i.e. asking questions about extremes, which the whole world is increasingly about, is a non-trivial world, all right? So, we can solve this. If I have data, IID data, I look at the maximum, and if I can find normalizing constants, whatever they are, so that I have a limit distribution, like in the central limit theorem, but now for the maximum, then we use this standard notation, F, which is my data model. I don't know the distribution. I may have a model, I may have estimate. F is in the maximal domain of attraction of this limit distribution. The maximal domain of attraction, it's like the data in distribution are attracted to that model in my left pocket. The H's are in my left pocket. Now, what are the magical distributions in my left pocket? Perhaps the Gaussian. Believe me, it's not a Gaussian. Although in industry, still every moment of this day are still trying to convince some of us that, well, we can use the Gaussian model, even talking about extremes. It's wrong. It's totally wrong, all right? So, so what does this H look like? Well, here it is. So I empty my left pocket, and you got all the models. There is no other model out there that gives you the normalized limit distribution of IID maxima as those here. Modulo location scale. I can always change the location of my models, and I can also always scale. So I can replace x by x minus mu over sigma for some mu, some sigma. I'm not talking about mean and standard deviation here. So forget about location scale. We always look at standard model. And how does it look like? Well, it looks pretty explicit. That's still good news. Remember, the Gaussian distribution, stable distributions for the sums, you cannot write down the distribution function explicitly. Here you get the explicit distribution function, driven by an important parameter psi. It's called the shape parameter. That's the parameter you're after. And this can be anywhere in R, and the model is written in such a way that if psi goes to 0, you see the famous Euler theorem, you get this double exponential. Now you see already you get very strange, different distribution functions. If you never have seen them, you say, oh, well, that's cool. And it's very different from the Gaussian, all right? And so if psi is negative, you have to be careful because this has to be less than 1, so you need this positive. You can say, well, that's a little comment. Well, no, that's not just little comment. That's highly disturbing comment. Because now you see that for negative psi, which is, for instance, just accepted often for rainfall data or meteorological data you encounter, you see that the distribution function you're looking at, where it's non-zero and 0, depends on the unknown parameter. That maximum likelihood theory doesn't like. Because that introduces non-regularity possibly. So statistics, I said there's quite a lot of, no, well, call it bad news. We can solve it, but you think carefully. So let's not leave it. The main point is this class of distribution functions, modulo location scale, is the only class of distribution functions you can find that solves this problem. That's really a wonderful result. That goes back to Fisher and Tippett in the 1920s. So nobody can say we didn't know about the non-Gaussian world. No, the non-Gaussian world, the world of extremes, goes back to the 1920s with Sir R.A. Fisher, the founding father of modern statistics. So it's really there. And of course, they worked on it because it was very much an issue of importance. I mean, one of the early works that people looked at is the strength of fibrous material. I think it was even one of the early papers was on wool, the strength of wool. So if you take a piece of wool in spinning, and you stretch it, so it has fibers, and you stretch it until it breaks. When does it break? When the last breaks, not when the average thread breaks. That's a Gaussian. No, it breaks when the last fiber breaks. So the extreme value question was extremely natural, and that's how Sir Ronald Fisher and Tippett wrote the early paper. So they discovered versions of this. Of course, there's a whole school that then went back to that. Okay. The names you have to remember. So in my right pocket, sums, the Gaussian, the stable distributions. Everything to do with sums, averages. In my left pocket, it's the Weibel, the Gumbel, and the Frechet. The Frechet is for us the most important. That's why this is orange-colored, because that's very often the model we encounter in finance. The Gumbel is a double exponential. The Weibel, the variable always has a finite upper endpoint. So if you have data which have a clear upper finite endpoint, the beta type distributions, the Bernoulli distribution, just name it, just finite upper endpoint, that's immediately the variable model. All right? It's not clear if I say, well, which of these three limits corresponds to the exponential, to the log normal, to the Gaussian, as if my model for the data. So if you look at let's say, log normal data, which is the standard model in finance, log normal returns, geometric Brownian motion. If I start with, you start simulating, and we can't do it now, unfortunately, but just simulate log normal data. Look at the maximum, normalize it, we'll tell you how, and look at the shape of this limit. So look at this here. What happens here? I can tell you, after a while, if you simulate, but simulate a long time, I'll come back to that, you will see this maximum normalized finally settle in a distribution function which looks like this here, which looks like it's skewed to the right, it's two-sided, it's the Gumbel. So if you're interested in finding maxima, behavior of maxima of Gumbel, of log normal distributions, believe me, this is the shape, the limit shape you find. So in my left pocket, I must pull out the Gumbel distribution, and if you want to talk about the extreme events related to the log normal, that is the limiting model you use. And that's kind of magic, isn't it? But why would that be? The same would be true with the exponential. The same would be true with the gamma. Not the same is true if you take the Pareto. Not the same is true if you take, let's say, the uniform distribution. That's where things become difficult. But anyhow, let's... So now the question is, what kind of data correspond to what kind of limiting model? And now I come back to the early statement. In IID data with finite variance, the Gaussian distribution, the normal, is always the limiting model for sums, always. And here already you see there will be differences. So the whole part of the theory is understanding that. We'll just do a bit. So this is the famous Fisher-Tippett Theorem. In words, it's just saying the models I wrote down here, these are the only possible limits you can find. So this is like our Gaussian stable universe for maxima. You can't find any other limiting model. It's nice now to stop and give you a couple of hours. I cannot give you the full proof, but an idea of the proof, because it's one of these magical results. Anyhow, not in this course. So I even say it's non-trivial. Quite a lot of work. Okay. So these are called the generalized extreme value distributions. That's a name. Never mind the normalizing constants. We come back to them later. We can always choose them that we have the standard form. Okay? No location scale, that's a detail. Now comes a very interesting statement. All commonly encountered continuous distributions are in the maximal domain of attraction of some of these, of one of these. But it's commonly. So if you can test me, we will not do it. If you mention a distribution, the Burr, Fresche, the exponential, Gumbel, the uniform, Gumbel, the log gamma, Fresche, whatever distribution you throw at me with a name, I can tell you what is the limiting model you take out of my pocket to solve extreme value questions. Now somebody says suddenly, Poisson. You mentioned Poisson. You didn't, but let's say you would mention Poisson. No, that I cannot treat in standard theory. That's pretty amazing, isn't it? The most important discrete distribution doesn't fit in my theory. Geometric? No. Negative binomial? No. Mainly extreme value theory for discrete distribution, i.e., if you do an experiment, let's say bioassay, in biology, and you look at counts of let's say, particles in the system, or counts of a typical bioassay, and you won't say, that, oh, I'm interested in the maximum question, the maximum number of counts when you do disease modeling. You cannot use standard theory. You must come to me and I will tell you where you have to look. This is intuitively a little bit clear, because talking about the maximum, you must define the maximum. The problem with discrete distributions, you may have with two independent ones, identical observations with probability strictly positive. And so that means, how do you order data? So just a general comment, with the commonly and discontinuous, be careful. So if somebody comes to you and says, and of course in finance, it's typically in credit people use in discrete models, even Bernoulli models, default, non-default, or use Poisson models. Be careful, all right? So that's our judgment. In the continuous case, everything is fine. Now you can work it out. I will not do these exercises. You can do them yourself. Everything is on the slide. Let's say I take a Pareto distribution. There are many versions of the Pareto with parameter theta, so x to the minus theta. Kappa is a parameter. So it's a typical power law. These are the bread and butter models in modern finance. We all know that the world out there is power-like, not Gaussian. So it's x to the minus theta. When we give you the norming constants, you can ask me, how do you find them? I give them. There's a whole theory for that. And you see, this has nothing to do with the norming constant with mean and standard deviation. They're just different, which is also natural. And you do the calculation, so you want to see, go back to this here, does this converge to the limiting form? If it does, fine. Find the limiting form. If you do the calculation, I'll leave that to you tonight, and you will see you get the Frechet out. I already said Pareto goes to Frechet. So just do this little exercise. It really shows you how these standard models come out. You could do the same for an exponential if you can guess the normalized. The exponential, you can guess the normalizing constants. You'll find the the Gumbel. Okay. This is a slide, I just want you to have heard about it. First of all, I want you all to remember when you walk out of this room, one famous mathematician that very few of you know, Jovan Karamata. Who has heard in this audience about Jovan Karamata? One, well, two, three, some of them. Some of you might have been in my courses even. Jovan Karamata. Karamata delivers the mathematical theory for understanding a lot of the structure in the background of what the extreme value theory and also the sum theory is all about. It's all about slowly varying functions. Forget about it for this course. It would bring me too far. But my friend and colleague at Cornell, Sid Resnick, he once wrote a paper and with the title, How a Slowly Varying Function Can Ruin the Risk Manager's Night Sleep. It's there. I will say it has to do with rate of convergence. So there's a definition here. Think of a constant, think of a logarithm, but I will not go into detail. What I want to mention you is this theorem. Boris Vladimirovich, I think correct, Nidenko, one of the former colleagues of you at Lomonosov, he wrote a fundamental theorem in 1943, I think, where he showed that F is my data, are your returns, are your losses, your data, is attracted to the Frechet psi positive, one of the left pocket models, if and only if, that's what we like as mathematicians. These are the nicest results. If and only if my data model, F bar, is always 1 minus F. I look at the right tail. So the probability of having a loss larger than little x in my data model is a power, x to the minus 1 over xi, with this magical Karamata function, slowly varying function. Think of a constant, asymptotic constant, think of a logarithm, but believe me, I can think of many more complicated models, but they all vary slowly, much slower. So the main part is that. This is even only if. The whole of finance basically lives in this world. The L function is going to ruin your life. I remember a telephone call we started to introduce extreme value theory at Risk Lab to finance in the mid-90s. And one day I get a telephone call from a trading desk in London. I still know the bank. It's not important what the bank is. They said, well, we are sort of pricing options based on derivatives, options based on extremes, like a McGrape option, or some option where the payout is a maximum over several underlying, so it's a maximal question. We do simulation. But I said, it converges very, very slowly. I said, yes, that's a problem. Extreme value theory from the model, from the data, the maxima normalized to the model in the limit, this can be very slowly. And if I say very slowly, I mean very slowly. As slow as I can make it by changing the L. And you don't know the L in practice. No way. Let me tell you, if you want to look at convergence for the exponential, it's like lightning. You're immediately in the limit. The Gaussian extremes goes fast to the limit, the gumbo. The early Pareto goes fast to the limit, the one I showed you. Believe me, if this were their data, in no time you're in the limit. If, however, Vladimir comes to me and said, no, I work with the log gamma. By the way, the log gamma is a standard actuarial model for insurance claim. There's famous papers by Nordberg and Ramlo Hansen in the 70s, 80s on glass breakage and windstorm damage. The log gamma. It has a power tail. But now the L function is pretty unpleasant. A logarithm. You can say, so what? Well, you simulate. Now it also goes to the Freshe, but very slowly. You need loads of data. The T, the right tail of the T distribution is a power. There, the L function is like asymptotically a constant. It goes very fast. You see, that's a problem. I just want to mention that if you look at the central limit theorem, convergence is always the same rate. You have this 1 over square root of n. You can look at Berrier-Seen, etc. It's uniformly fast. This completely depends on the underlying assumptions. Asymptotically, you don't know this in practice. So this is already one thing you have to take away with you. And I cannot help it. It's just one of these little boxes you have to open if people talk about extremes. A warning. It may converge very slowly, and I can't help it. Okay. This theorem already brings us to a first important tool. I just briefly mentioned that, and we'll see later when Marius takes over, and I must definitely stop in time. We'll see. Just to tell you, I can open a little door and say, look, you just peep into the room, and there's a statistical technique there. This is called the block maxima method, and it comes from environmental science. You look at your data, x1, 2, and I call it the data length. I call it later little n times little m. You'll see why. Here I have 12 observations. Now I divide my data into blocks. So you see a first block, you have 12 observations, a first block of equal size. 3 of them, 3 of them, 3 of them, 3 of them. You may take your financial data and you do yearly blocking. 260 or 250, 260, 260, 260 observations. Or you may do quarterly block, whatever. So you block, and now you see why it's going to environmental science. In environmental science, the blocking is natural. You have seasons. A yearly blocking, a quarterly blocking. There's a kind of a natural blocking in environmental science. I do assume that everything is IID. I might do beforehand some, if there's really non-stationarity, as you saw in yesterday's in Alex's data, the ozone level, or I think it was, of course you first deseasonalize and so on, and do extreme value theory on the residuals. IID. Now, for each block, let's say this is a year. I only have 12 observations, but let's say this is a year. I look at the largest. The largest observation of my 3 data points in the first block. I look at the largest in the second block, the third and the fourth. So I reduce remember, I'm after a model for extremes. Of course, you can say, well, I've got my data, look at the extreme value, and then you have only one observation. Now, even if you're very, very optimistic, doing statistics based on one observation, you shouldn't. That's where the blocking comes. So let's make several versions of the extremes. Here I got 4 of them already. Now, within each block, if I have sufficient data in the first block, let's say 100 or 260, the largest of 260, I may already have a limiting model. So I may have, in each of these blocks, that this red maxima can be approximated by a distribution in my left pocket. Let's say one of the fresh airs. If so, then at the red level, I have IID data from one of these left pocket models. Let's say the main parameter is xi. Then I can do maximum likelihood. Because I know the limiting distribution, normalized. The normalization I can take care of, don't worry, statistically. And I can estimate. I can estimate maximum likelihood. Now you see the main problem. You want at the same time enough data in each block, because you want that the distribution of the red is close to its limiting distribution. That's where Fisher-Tippett enters. Okay, so you want to have enough there. At the same time, you want to have enough red maxima. So you want to have enough red blocks. Why? Because if you look like that, you do maximum likelihood theory. And maximum likelihood also bases its results on asymptotic theory, if you do confidence intervals, improve efficiency and all that. And then you still hope that everything is regular. Believe me, little comment, if xi is greater than -0.5, the world is fine. Close the parentheses, all right? All data I have seen, I personally have seen, xi is always greater than -0.5. Xi negative, the variable we typically find in environmental data, or data that's clearly constrained at the top. The data I often see, very often, always see in finance and insurance is fresh xi positive. So the likelihood works. But now you see the problem. You won't have many blocks, and each block many data. But of course, you only have 1,000 observations. These two fight. And that's a typical variance bias discussion. There's no easy solution. We will see that later, surely, perhaps in the examples. I'm promising a lot in your direction, Marius. You better start working. All right. So I think, but I hope you'll really see, with this one theorem, I can already do stuff. Okay? When I do that here, so this is the theorem. I look at the maximum. I normalize correctly. Suppose I know them. So I have to subtract and divide on the right-hand side also. And when I write that, I do statistical approximation. I say, okay, I know in the limit, this is an H with a xi, and of course now I've got here location scale. Now you see, I forget about the normalization. These are 2 extra parameters. N is fixed, all right? So you see that I've got now, the limit is the xi, which is a shape. There's a location parameter, let's call it mu, and a scale parameter. So it's a 3-parameter, explicit 3-parameter distribution, the good news. Not like the Gaussian or the stable, alpha stable. So now, at the level of the red, I now do the fitting, maximum likelihood, and I get estimates out, okay? You can write down the likelihood, because I can write down the density. You can do whole likelihood theory. It's explicit, so it's straightforward to program, well, to write down. It's not straightforward to do the optimization, because these distributions are difficult, and except with xi negative, you have to be careful about regularity. But it can be done. So I can write down the likelihood. These things I've mentioned, and there is no general best strategy to find the optimal block size. It's a fighting between bias and variance, which you often find in statistics. For instance, if you do spectral analysis for time series and you want to find the periods, it's always your window carpenting, broad window, narrow window, variance bias. The whole of statistics, interesting statistics, is full of variance bias questions. That's a theory. Now, what are your questions? You like to ask me, well, give me for my data, let's say the standard temporal, so many data, give me a 1 in 100 year return estimate. And you come to me and say, I want to find out what's the probability that next year's data of your model you're looking at will be a record. Even the Olympics, there's a very nice paper on the Olympics. For instance, what is the probability that a massive record-breaking in one of the field tracks really fits to some extent in the previous data? I'm very careful in formalizing this question. Is this acceptable? And I will not give examples, although I have examples. Is this an acceptable record given previous data? Right? So that's a question of record. These are your questions. These you can answer. Now again, I will go fairly fast through this section now, but I just see that the kind of questions, and Marius will come back to that later. You can look at the level based on this theory. You can start answering the following questions. And believe me, if tonight you sit down and you just read through these slides, or in the book at the relevant section, you'll see it's fairly straightforward. But then let me just concentrate on the question. Say you're interested in the level R and K, which is expected to be exceeded in 1 out of every K blocks of size n. Each block is size n. I have m blocks. And now you ask, for instance, well, what is the level of my data which is expected to be exceeded 1 out of every K blocks of size n? This means, if you think about it, that your maximum larger than R, this is the maximum of one block, larger than this number you're looking for, it's like dike heights. It's like constructing the dike height, is given small. For the Dutch dikes, the K was 10,000, 1 in 10,000 year events. The block was yearly data. And the Dutch constructed their dikes after the 1953 disaster with the Delta project as a 1 in 10,000 year event. That's a kind of question. So you bring it into the language of mathematics. Here it is. For this, you use your asymptotic theory. You can do, because you know how to approximate the maximum. Here it is. You take 1 minus, 1 minus. This function you know explicitly. You estimate the parameters. So you put little hats on these things, maximum likelihood, and you've got a solution. Okay? It's there. Go through it easily, but this is really first-year probability calculus. Very easy. Okay? And here is the estimator. If you invert, this is nice, because I know the distribution H explicitly, not like in the Gaussian case, and so I can explicitly invert. So this is your estimator. You give me your K, I estimate the psi, the sigma, and the mu. This is your estimator. And you can do, because it's maximum likelihood, you can do asymptotic confidence intervals. But there is more to that story than I can tell you now. But you can also look at the frequency of an event with described size. It's called the return period problem. This return level problem. And again, you can do the same. I'll leave that to you. We might have an example later. But this is the kind of questions you can answer. Or you can look at what's the probability that next year's, if I say next blocks, the first future block, if it's yearly blocking next year's, is a record. That's a statement of maxima. So you can all work this out. You know the explicit distribution in the limit. You can invert it if necessary, estimate all the numbers you get. Yep.
For that
Dike
theory about the dikes, what psi would they have got with that theory?
I forgot now. No, okay. Okay, this is a big, in German, es ist ein Klammer. It's a big, no, I think the original models they came up with was a Gumbel model. Original model was psi 0, original data. Presupposed as psi 0. Then later, of course, in the initial case, because a 10,000 year event, the Dutch, of course, are it's much more than just estimating IID data. It's, first of all, what is the dike height? What are your data? There's a C search and all that. They used extreme value theory. They knew they would not be able to get reasonable answers based on the Gaussian. So that took at least a maximum approximation, and I'm pretty sure the original estimates were xi 0. I can look it up. It has now been updated quite a bit also with the greenhouse effect, but it was a combination. I think it's an excellent combination. And may I take the point there and we can discuss in the break more about it?
That's fine, but I'm asking for a particular reason, because that's a classic example where from physics you are certain the distribution must be limited.
Well, you see, xi 0 is already... That's a good point. That's a good point.
I'm making a point for insurance, because in insurance we have the same situation.
Now we can enter in a I understand, Michael. This is a... No. This is like the statement we have in extreme value theory. Because of data, we often have infinite mean models. Surely everything is finite mean. Surely there's an upper limit. But are you happy to give me the upper limit? Is it the sea surge is 3 meters, the sea surge is 5 meters, the sea surge is 10 meters, like in the Sendai flood? The problem... No. That's the whole point. Once you start setting your upper limit, it really influences a lot of the... So I personally would not put an immediately a priori limit. You can say the limit is 10,000 meters, which I'm pretty sure is correct. That is not far away from having an upper-ended... I understand the question. Can we come back to that perhaps also in the break? It's a very important question. It's a very important point. I think we should continue. We should continue because we have no microphone there now. So it's a very important point. Let me make one bracket, and perhaps you were not allowed to teach anything, but no. I had this discussion very often on the upper limit. It was a big discussion on operational risk. I now make it big because it's a very important question. Operational risk in the beginning was the same question. Surely it's limited. If you have a bank X, and I can again use a name for X, surely the limit is, let's say, the total balance sheet or whatever, multiplied by 10 even, whatever. Or the wealth of the world. There's an upper limit. Yeah. But now the question is, what upper limit do you put in your data? I say, well, let's do it an upper limit of 10 billion for bank A. And I know the banks that did it early on with extreme value theory. It turns out that where you put this upper limit is highly determining the estimation procedure. I personally would not do it, or I have to really have a God-given upper limit by construction of a derivative or so that I know that's the limit. The same thing is true if there's a big discussion, if you look at the model, if xi is greater than 1, then the model is infinite mean. Now you can say, well, infinite mean, how can you do in insurance infinite mean? I can tell you there's a lot of models out there, data that point statistically to infinite mean. I'll just run the statistics. Also operational risk. I'm not saying that I believe that the best model for operational risk is an infinite mean model. I'm not saying that. Infinite premium. I'm saying if your data in a careful statistical analysis points to an infinite mean model, then you better take a step back. And then you say, if this is the portfolio I'm looking at, if these are the data I'm working with, I should be very careful by automatic pushing a button and say, these are the estimates. This is your value at risk. This is your, well, not expected shortfall, doesn't exist. And the same question you find in environmental statistics. Environmental pollution, take Exxon Valdez and the later events in the Gulf of Mexico. Many of these data, take a nuclear risk. Now my experts are sitting in the back. Nuclear risks, the 1 over xi is typically 0.7, is infinite mean, 1 over xi, 0.7. So xi is greater than 1. You should really think carefully risk managing that. And there's Marty Weissman in Harvard. He wrote an interesting discussion, but it's hotly contested by economists. You know, the economists are very good in really attacking each other. It's called the dismal theorem. Write it down, look it up. Look at the discussion. It's all about the questions you mentioned here. And the main point is, Why do we get these situations like environmental risk, like catastrophe risk, like well, many examples, nuclear risk, these very heavy-tailed models, extremely heavy-tailed, infinite mean, infinite upper point, you really step back and they don't have the classical solution. At some point you would even say, is this the right way ahead with society to go into developments that create these kinds of risks? They may not anymore be insurable. You see, it's a very big societal question. The Dutch solved it brilliantly for there, but I must continue. Sorry. But it's a very important question. Okay. So I'll leave this example. You can. The point of the well, let me give you the story. Alex wrote this example. I still remember very well. We're still working at Risk Lab. He wrote the example as a pedagogical. They say you take a risk manager sitting in his or her office. It was Alex, so in his office, and he's looking at the screen. He said, "Oh, by the way, it's Friday the 16th of October, and my God, this has been a very turbulent week. Today, the S&P dropped by 5, etc%. The largest drop that week was 9, etc. This was the largest drop since 1962 of the S&P. What happened in 1962? What was the world facing in 1962?
Cuba?
The missiles. It was Kennedy, the missile crisis with Cuba. So this was a very hot week. What's going to happen next Monday? I'm not going to say, I'll predict for you exactly what will happen on Monday, but let me see what the data tells me. This example is about that. It uses the notation I introduced. I will just quickly give you the gist of the story. We do a point estimate based on our data, block maxima, for next Monday. What's coming out is a 4-point-something estimate of a return drop-down. That's okay. What happened on Monday? The number is there somewhere. On Monday, we had a drop of over 20%, the famous Black Monday. Now you can say, oh my God, extreme value theory is not working. You said 4 or 5%. It was 20%. Wait. This is statistics. I give you the confidence intervals. If you now believe in Gaussianity, you say, well, no, it's 4.7% plus minus 2%. You're still far off. If you now do extreme value theory based with likelihood theory confidence intervals, you find a confidence interval going from perhaps order of 3 to about 20. That's extreme value theory. And now I'm saying to you that shows you that extreme value theory opens your eyes and says, this is a damn difficult question. But at least the best of my statistical knowledge, there is non-statistical knowledge because we knew what was happening with portfolio insurance on Black Monday, well, the week before. They were all running for the same exit door. We're saying, well, on the confidence level, it allows us going up to 20%. And then we're not far off. You see, extreme value theory is able to catch that somebody was, this is a once-in-a-lifetime of the world event. And again, I know several CEOs of big American companies who said that. It's wrong. With the right model, this may be a 50-year event or a 2,000-year event, which is quite different. That's on that slide. And this uses this theory of block maxima. I must move on. Threshold exceedances. Rather than looking at the picture I saw before, I can look at this picture. These are the same data, but I don't use block size. This is statistically the more relevant method now. I look at the high level. Still IID data. Sorry, I'm sort of fast forwarding in your slides, but I will fast backward later. So now these are the same data, but I don't look at the maxima. No. I said, let's move up in the data and look at the excesses, exceedances over a high threshold. I always called exceedance the points in time where it happens, and excesses is the size above it which happens. Okay? Surely, extreme value theory, you want to understand that here. And already Mario said yesterday, well, if you have IID data, these points when this happens, if you go high enough, it's Poisson. That's famous Poisson's theorem of rare events. a key theorem. Mathematics gives you, and that's much more complicated, the convergence of this whole process dynamically in time and space. That's a famous Ledbetter theorem. We don't even treat it in the book, but we can do it. That's a power horse of extreme value theory. So rather than looking at blocking, which is natural in some context, we look at high levels and try to understand what's happening above this level. These red peaks, can you describe them? Yes, we can. Famous theorem, here it is. Even in a very applied course, I like to write down theorems correctly. It may be very annoying. But what this theorem tells you, without I haven't introduced any notation, it tells you if you look at the distribution function of your loss conditional on having a high loss, so this is a distribution function of the red excesses, okay? This is a distribution function of these things here. So you're given you have an excess. How high is the excess? So you give it a distribution function of these conditional losses, conditioned to be above u. This theorem tells you that, sorry, I'm now getting confused myself. This theorem tells you that there is a, sorry. Oh, it's horrible. This theorem tells you that there is, again, something in my left pocket. I can give you an explicit distribution function that approximates the red sizes. And then you say, well, that's great, because that's exactly what I want. And this distribution function is written on this slide here. So it's an explicit distribution, the generalized Pareto, the GPD. And now I know of thousands of papers in finance, GPD everywhere. Why? If you have IID data and you're interested in these conditional excesses, the red peaks, their distribution, the limit is a GPD. Nothing to do with the Gaussian. It's not in my right pocket, it's in my left pocket. It's a GPD. And now, of course, you see, well, now I can do maximum likelihood theory again. I can build up the whole thing. But let's revisit the theorem. I said it's a theorem. The theorem tells us that the distribution of the little red peaks, this conditional distribution above this high level, if the level goes to infinity or to the upper endpoint, so I better go higher and higher in the data. This is GPD. And then we get something nicely mathematically thrown in that it's uniformly, but that you get as a present. That is nothing special here. So now, if you look at the world, and this current statistics of extremes looks at this approach. Current statistics of extremes looks at this. Why? Because the blocking is not really very natural in many applications. So you look at your data, you look at the conditional extremes, and you model the conditional extremes. And now I go back. Well, let's now write down the definition. It's here. So you're interested in this is the red distribution. We should have used the color red here. Given that you have a loss above the level u, what's the distribution of the excess? So the loss minus the level. This is the red peak. So that's exactly the thing that appears in the theorem. The theorem is Pickands-Balkema-de Haan. Pickens on the one side, and Guus-Balkema and Laurens de Haan on the other side. They proved the theorem independently in the 80s. And of course, this distribution I can easily write down. I can link it to what we now call the expected shortfall. Careful, but you can look at the expectation, if it exists, of this distribution. So that the conditional loss, given you have a high loss, the expected shortfall, this u is there, or you just add it up. This often is also a difference in thinking between finance and reinsurance. A reinsurer, I normally do a reinsurer, if the reinsurer here says, well, no, I'm excess of loss. I'm interested that my risk pierces the u level, and now I'm interested in a fair premium, what is the expectation of the excess loss? That's what the reinsurer is interested in. In finance, if you don't have anything derivatives there or insured anything, you'd bear the whole loss. So a bit of thinking differently. So without the u, it's expected shortfall, and you see expected shortfall is so naturally there. That's why from the beginning, well before many of the papers, we had an expected shortfall in all our courses. And I still remember giving a talk to some banks in Zurich, some famous banks in Zurich, on extreme. They said, why don't you look at these kinds of things? This was well before the expected shortfall discussion. It's so natural. The expected size above these levels. Okay, and now you can work out everything, the statistics. I will not do that. It's not going to help you. This works, you do the statistics. Again, you can write down the log likelihood. You look at your red peaks now. You don't look at your red dots, the maxima. You look now at the red peaks. The red peaks in the limit, again, properly normalized. I wipe some conditions under the carpet because there's this beta u here. There's this scaling parameter, but never mind. And by the way, sorry, this holds if and only if this condition again holds. So the two theories, Fisher-Tippett, block maxima, peaks over threshold, they have the same mathematical conditions. It's the same way of looking at the problem mathematically, but very different from an applied point of view. Current applications of extreme value theory are completely in this field. It's all about peaks over threshold. It allows you much more flexibility. You can make this level U time dependent. You can make your parameters time dependent. You can do that also in the block maxima, but it's much less natural. So this is the current approach for most of the application of extreme value theory. So you look at your data, you choose your U. How? Well, it's just choosing the U, because it's a limit theorem. U goes to infinity, if it's an xf infinity. Where do you choose your U is as difficult as how many blocks do you take. It's exactly the same, mathematically. There is no standard solution, whatever people tell you. Some papers claim they solved it, bootstrapping, resampling. It can help you, but there is no standard really solution to that. It's your decision in the end. Okay, let's now, you can write down the likelihood. So you look at your excesses over this threshold, the number of excesses, you write down the likelihood, you estimate, you use a lemma. There's an interesting lemma here, and again I will say it briefly. If you have exact Pareto data, exact power tail data, then this mean excess function, this expectation of the loss size given you have a high loss, is a linear function. The GPD has that problem, psi positive. And even if it's linear from a certain point onwards, it's a limit result, it stays linear from that. That's written down in this lemma. I skip the lemma now, it's very important. Well, let's look at an example. How do you estimate? So this mean excess, the expected excess loss size, the expectation of the red part, given that you exceed, that's an important function. Clearly it's an important function, right? It will be the fair premium in excess of loss reinsurance treaty. That must be pretty important, all right? How do you estimate it? Trivially. How do I estimate that? Well, I look at my data. Let's look at the data here. I look at the number. So I look at the number, I sum these excesses, and I divide by the number of excesses. That's all. The empirical estimator, all right? I got capital NU of excesses. That's a number of excesses above U. It's random. Depends on your data. And then I average these red parts. The easiest of the easiest. Well, here it is. That's your estimator. So if you want to estimate at the level V, you look at the excesses above V. V is typically larger than your initial value U. You only count the red parts, and you divide by the number of red parts. That is the indicator function. And this function now you plot as a function of the order statistic. Now you plot this function. Of course, this function you can only plot if you have data. So you look at your data, order the data, and then calculate this function. Okay? If this function is linear from some point onwards, we feel, psi positive, we feel that we are not far away from a Frechet. And because in the Frechet, the Pareto, generalized Pareto, it really is linear. I know I'm going very fast. But I really want you to understand the gist of it. I said, in 1995, we gave a whole week a course on this. So, okay? But it's the same problem as finding the block size, the U. I can help you in starting the procedure. So here is an example. I think I'm okay in time, isn't it? So I still do this, and then you take over. All right. is a famous data set, the Danish fire insurance data. Because I think it's much more important if I talk to you about data. But I hope that you understood first a couple of things. If you're happy with using the Gaussian distribution for solving problems in statistics related to averages, and I think you're all happy with doing that, with finite variance, then you must be happy, that's a causal implication, by using the GPD for IID data if you're interested in excesses over high threshold. Otherwise, I've got a serious problem as a mathematician and understand how you think. What I may not agree on, or you not on, that the kind of questions you ask for sums are perhaps easier to swallow, whereas the kind of questions you want to ask about extremes, extrapolating beyond the data, because now I suddenly have a model that allows me to extrapolate anywhere, that society is often using this theory a bit too quickly, thinking it will solve its problems according to extremes. And the whole of the world is, unfortunately, at all levels, about thinking about extremes. That's why I say it's finance. I would say it's society, political science 101. We must be able to understand what it means at looking at extremes, what kind of behavior they have. If you take away that from the first part, I'm happy. And you take away that there is theory at the level of the central limit theorem, the same thing that helps us. Here are some data. We know about 2000, this is real data. It's already in our yellow book. This is Danish fire loss insurance data. It's losses in Danish kroner. It's an old data set, but it's a wonderful data set. Losses to industrial dwellings. And we only look at, okay, these are the data. They're all discounted. They're in Danish kroner. You see, it's old data. And now they're all put back to deflated. In those days, inflation still mattered. They're deflated to 85 prices. Here are the data. These are the data. And these are typical data. If you look at log returns later, these are typical data. Well, I think I better look at extreme value theory, because more than 2,100 observations. So most of the, well, I would say non-action is here. Nothing much happening. But suddenly you get these huge losses. We have analyzed the data, reanalyzed. Alex did a lot of work on these data. The data in the recent version are I think, I think it's even on our repository, isn't it? Well, Alex has all the data on his website. He's quiet.
Danish is in the repository.
Well, it's available. It's public data now. It became a very famous data set. I think it's as famous as... What's the most important data in multivariate statistics? Every course uses them in that data set. Well, let's say in discriminant analysis. What's the most famous data in discriminant analysis? Goes back to Fisher. The Fisher data. Wow. The Fisher iris data. Iris setosa, iris versicolor, iris virginica. The standard data set in discriminant analysis. Linear, nonlinear. This is becoming not that level, but I think the Danish fire data has become a standard data set in extreme value theory. Here it is. Here's the mean excess function. You can all do it. You can start doing it by hand. Of course, you need a computer to really do it fully. So I look at the level 10. I look at the level 10. I average all the losses above level 10, and I divide by the number of losses. That's the value at level 10. 17, say, I forgot now. Not important. So you can draw this picture. Here it is. First thing, the picture is increasing. I'm going back to your question, Michael. This is increasing. What does it mean for a mean excess plot to be increasing? So it's an estimate. Pareto is exactly increasing. The expected excess loss above increasing levels is increasing. Now let that go through your mind, even early in the morning. The higher you go in your data, the higher the excess losses are in the mean. They keep on growing with the... Now you understand gradually what it means. We're in a very dangerous world here, this kind of data. And this goes back slightly to your question, Michael. It's a data, if I have it in my book on extreme value theory, a nice data set in that book on insurance shows that it's not increasing. At some point, these points are going down. That's a typical example where the gaps are getting smaller and smaller. But here, I don't see that. All right? So this is pretty Pareto. Of course, it's not fully Pareto, because there's curvature here. Now, here are perhaps 2,000 observations, so every curvature you see is significant. You can do regression testing, whatever. It's significant. So here, I'm not yet in the limiting attraction of my model, the fresh air. I'm not there yet, because it's not linear. So I would presumably from here, these are always all over the place, because there are only a few data points. If my level is here, I only average over 1 point, so you get a lot of variation. But this here, so where would I put now my initial U? Well, let's say around 10. I think I've got this initial curvature, and then I think this is pretty linear. By the way, that's eyeball expertise. And the point I make, there is no standard solution you can bring to this. We can only help you in deciding where to start an analysis, but I surely would do the analysis and redo the analysis at various other points. This is the fit to my conditional distribution, but this is also the fit to the real distribution, modulo a constant. So you see, my fit really goes nicely into it curves nicely into the tail. But the little point here is, I fit only above 10. I took U equals 10. In the beginning, I got a lot of discussions, and people say, well, why do you fit, if I look at my fit below here, it's horrible. I say, I'm not interested. I'm not interested in fitting the data in the center. I can do that. I can just check, smooth the histogram. In some cases, of course, you want a model that fits from 0 to infinity. I only fit the tail here. That's important. And now, of course, I can do whatever I like. Let me move on. For instance, I'm interested in the tail of the distribution. Well, the tail of the distribution function, that's a definition. I rewrite the definition now in terms of the conditional distribution. That's trivial algebra. I subtract the U, and you see I get the tail of the data, so the probability of a loss larger than X is the probability of a loss larger than U, times, given that I'm larger than U, that I'm larger than X minus U. It's a one-line algebra. Every detail is there. This is first-year probability. Not even that, I think. And now I say, how do I get an estimate of the tail? Well, here, you put heads everywhere. This one here, the best thing I can do is put here NU over U. Oh, we haven't written it down. So I would estimate this by the number of excesses divided by little n. Nothing much I can do. If I have 7 excesses out of 12, it's 7 over 12. Here, I estimate it, so I assume I have exactly, this calculation typically holds only in the limit, but it's exact. I assume I'm really in the limit model. This I can estimate. If U is large enough, I know it's GPD. Exact here, or in asymptotically, I've got the limit. So you see, immediately you get it. If you're interested in the tail, you get the tail. Why would you be interested in the tail? Because you want value at risk and expected shortfall. You invert it. There are the formulas. These are the exact formulas for the expected shortfall in value at risk. In the exact model, in the limit, or you put quiggles here in the asymptotics. Alpha large enough. I remember I showed this to Wall Street as a general point in the late 90s. And I said, these are more relevant estimates of value at risk if you want to use value at risk. I even told them these days, do you really want to use that? And they said, nobody is ever going to buy that. I don't mean putting money on the table, but, well, perhaps also, but they never accept it. Why? How do I interpret this? If I go to a trader, you're a trader, so what's your xi? What's your beta? Think back of the Gaussian model. Remember the formula yesterday? The value at risk is the mean, which is very difficult to estimate, mean return, plus the sigma, phi minus inverse alpha. Remember? The sigma is the volatility. If I ask you your volatility, you know, because that's your heartbeat. Sorry, as a trader. The more it goes like that, the more you have problems with your heart. So you know the volatility. Here, none of these parameters I understand. I'm sorry, but this is the real world. I'm not talking about the fancy world of Gaussianity. This is reality. And of course, your estimates are very different. And suddenly, the XYZ CEO statement on this is way beyond the lifetime of the universe event, the 1987 crash, or the financial crisis, credit crisis. You know, in these models, if you use the right parameterization, just as a thinking, you come to models like 1 in 50, 1 in 100, 1 in 200 years. That should concern every CEO. Okay, so that's what extreme value theory is. And this we can summarize. You'd like to summarize that on the slides? Shall I continue? You're trying to chicken out. Sorry, can you just erase that statement? No. Okay, but you all should see. You sure you want me to continue without slides or not? Or no? I don't have too much, I think. Yeah. Well, okay. Anyhow, the point is you should be able by hand. That's the good news of EVT. All these limiting models are explicit in the distribution. It's not a density, an integral. It's a distribution. You can invert these. So these problems you can all write down by hand. If you go back tonight and say, oh, by the way, I want to find this formula, it's there. You can calculate it by hand. Okay, so you can do all the estimation. So this is now what I said to Wall Street. This would be your estimator. So you replace this by nu over n, the number of excesses divided by n. And in the GPD, you now do maximum likelihood estimation, which works okay if psi is greater than minus a half. Okay? And now you can do what we call profile likelihood, because you're interested in likelihood functions of this complicated combination of the psi and the betas. There's a standard technique called profile likelihood. You like to do that on... Shall I continue? When shall I stop?
In 2 slides.
Oh, in 2 slides, okay. So, well, here is now the analysis of the GPD, analysis of the Danish data. First of all, we go to log-log plots. Why do I go to log-log plots? If the tail is x to the minus alpha, the log of the tail is minus alpha log x. So the log-log plot is linear in alpha. So do a log-log plot, and then you see a linear line. Sloping line is pretty Pareto. By the way, a statistician, famous statistician, unfortunately he died, he once made a statement to me, he said, listen, there are lies, there are damned lies, and? No, log-log plots. The other one, of course, is also by Dove, I think, statistics, but it was true, that's the real famous quote. Careful with log-log plots. They turn everything Pareto. And I know some people that claim everything is Pareto. But still, if you do normal data, it curves like that. So here, I do now, these are above 10. This is my histogram. These are my data, the black spots, but on this new scale. This is my fit. And you must say, well, that's a damn good fit. That's not bad. I'm really I capture the data. The black line is my model. It curves only slightly. It's a wonderful model. That really shows, if the Gaussian state, I go back to my CEO of bank XYZ, he would have this model here. And then you have this observation. It's impossible. Of course, it was possible because it happened, but only once in the lifetime of the universe. Here it's pretty acceptable. Now comes a dangerous thing, because now we're becoming audacious. Now we can say, oh, wow. Well, this is log scale. I want the 1 in 10,000 event, the 1 in 100,000 event. Okay, you get it. Whatever you want, I'll give it to you. Well, now you look at confidence intervals. That's where the profile likelihood becomes important. Oh, it should be there. Oh, it's not there.
It is there, but it's almost not.
Oh, okay, it's there. But can you see it? It's on your... Look carefully at that. That's the same data. Now I estimate the value at risk at the level... let's say 95%, I think. This is the estimate. It's about, let's say it's about 40 here. That's my value at risk. You see this very faint curve here. This is Alex crafted this plot in the early days. On the right-hand side, this is likelihood theory. The 95% confidence interval, you can draw this line. You draw the so-called profile likelihood, whatever, standard statistics. You cut the line, it looks like a parabola, and this gives you the confidence intervals. The confidence intervals will be skew, and heavy-tailed. Skew, and not, it's rather wide because it's logarithmic. But let's look at expected shortfall. The xi here, I didn't mention it, sorry, is about 3. It's in the range of 3. The tail, no, the 1 over xi is 1 over 3. The tail is like x to the minus 3, like most of the standard data. Infinite fourth moment, finite third moment. Now let's look at this curve here. That's the confidence interval for the expected shortfall. The expected shortfall is estimated for these data as 58 million Danish kroner, with a 95% confidence interval going from 40 to 155. So you go now to your manager and say, oh, by the way, our expected shortfall, the famous risk measure, is about 60 million. But by the way, my 95% confidence interval is 40 to 155. Guess what will happen, all right? Again, that's exactly extreme value theory. It tells you, even for the nicest of the nicest data I know, it's real data, that extreme value theory opens your eye for estimating far in the tail, but it gives you also a feeling from how uncertain these statements are, and you need to bring other thinking into it. The Dutch dike builders brought, of course, other thinking to it. My engineering friends, of course, bring expert advice in the field of engineering and earthquake modeling. And Frank has always a difficult question.
No, I mean, this is great, because what you're showing is basically that in Solvency II, if somebody tells you, I have a solvency ratio of 200%, you can close your eyes and say it's plus minus 50%.
Well, depending on the model they use, I might do. It just shows you these extreme. Let's say if I were to move, I'm here still well in the data. If I want to move here, these intervals are all over the place to infinity nearly. Might even diverge. That's the reality. I hope you can still do a little bit with what I've done.
You can still say something about time series.
No, I'll leave the time series for the moment. You can do the extreme value theory also for time series arch and gauge models. But for very few of them.
Okay, thanks. Okay, so I just want to quickly point out some R scripts related to EVT. There is one around this Black Monday event that essentially describes the block Maxima method Paul described. And then there's one that reproduces the plots concerning the Danish fire insurance data set. What I would like to start with you, it's probably the only one we discuss, is actually something more theoretical. Namely, you saw the big results, you saw in the very beginning the strong law of large numbers, you saw the central limit theorem, so your right pocket. You saw the Fisher-Tippett Theorem and the Pickands-Balkema-de Haan. So I would like to at least convince you graphically in R that these results hold. These theorems are true. As Paul mentioned, the proofs are non-trivial, but maybe we can simulate a little bit, play around with it in R and see whether they work. Okay, good. So I simulate 50,000 observations of my favorite distribution, the Pareto distribution. This is now, as Frank mentioned yesterday, this is just one large sequence, 50,000 observations. The theta parameter is 3. Pareto 3.
It's like the Danish.
Yeah. Yes, yeah, like the Danish fire insurance data, yeah. Good. What I then built are the cumulative sums. So the sum over the first observation, first 2, first 3, and so on. And I divide by the number of observations. So I built averages over the data, over more and more data, and of course, by the strong law, I should see a convergence here. And this is the convergence, again, in log scale towards the mean. Yeah? So that's your strong law. That seems to hold fairly nicely. Yeah, Sn over n as a function in n, yes. Now, for the central limit theorem, I want to block that huge amount of data into different parts and then standardize each part, right? Location scale transform, and blow up with square root of n. And then I have realizations that should together follow a normal. That's the central limit theorem. So I take 500 blocks, and I split the data. I compute the true mean and the true variance in this case, and then I take the sum here and I location scale transform as was in the first slide on chapter 5. And then I can look at, for example, a histogram. So here you have a histogram of these location scale transformed and blown up with square root of n averages. And I overlay that with a density estimate, kernel density estimate, and then I also overlay it with the limiting normal distribution, standard normal. And that seems to hold quite nicely too. So based on Pareto data, probably location scale transformed sums follow the normal, right? Good. So nothing really new here. But then I can look at Knedenko's theorem, and I can now block in exactly the same way. I always use the very same data set, no different data set. Always the 50,000, I start with exactly the same data. But now I use these blocks, and instead of building the sums, I use maxima. So I build blockwise the maxima, and then I do location scale transform, so the Cn and Dn you have in the slides. And Knedenko's theorem is very nice because it also tells me how to choose the Cn and Dn. There's this one example that Paul gave you as an exercise to look through. The interesting part about that example is that the Cn and Dn is not as in Knedenko's theorem. Yet you get in the limit the standardized form of the generalized extreme value distribution, the GB. But the normalizing constants you get from Knedenko's theorem are very general. You can apply them to any f you start with. But in the limit, you might not get the standardized form of the GB. And this is also what we will see here. Because if I don't know anything about the distribution, or I don't have an educated guess as Paul what the normalizing sequences are, my best guess is to look at Knedenko and say, aha, my Cn is essentially the quantile of 1 minus 1 over n, and my Dn I can take as 0. And those are the normalizing sequences I take here. So I subtract the 0, the Dn, and I divide by the true quantile function, 1 minus 1 over n, essentially. So this is how I built my location scale transform data this time. So exactly the same data, just location scale transformed maxima instead of sums, and obviously differently location scale transformed, and I should get a GEV. And then this plot looks like this. So I have a histogram again, I have a density estimate, and I have a limiting, the corresponding limiting GEV density overlaid. It's a bit more tricky here. One might argue one would like to see this maybe in log scale or so. I tried this, but it's not as easy because of the histogram, and then also the densities can partly be negative, so there's a bit of numerical issues here. But overall, this looks quite nice, I guess. And then I can also look at the QQ plot, for example, of these location scale transform data versus the quantiles of my limiting GEV. So I also see something about the fit here. Right? This looks like that. Also looks actually very nice. Huh? We had a lot of discussions about QQ plots, and we showed also a lot of QQ plots since yesterday. Some remark here. It's always a bit difficult to interpret QQ plots without confidence bands. If you compare two QQ plots based on different sample sizes, it's not as easy to discuss where the fit is better because you don't have a notion of confidence intervals. And that's always important too. So there's actually an R package that can do that. It's a QQ test package. It's just a bit more complicated to use, at least at the moment. So, but that would also do the bootstrap we discussed yesterday and give you bootstrap confidence intervals. And that's then easier to interpret QQ plots, just for those that had questions about QQ plots yesterday. Good. But then that was a block maxima method, right? I plug up my data essentially along the x-axis, and I pick out the maxima out of each, and then properly location scale transform, and that gives me my GV distribution. But now I do the blocking, or not really blocking, but now I could do that along the y-axis, as Paul mentioned. So I look at the threshold and I consider all losses to be large or important that are above the threshold. So that then we are on the second approach to EVT, so in the peaks over threshold method. And as a rule of thumb, but this is very dangerous to say actually, as a rule of thumb, one typically takes like the 90% quantile. We had operational risk data where we had to use the 50% quantile because you have too few excesses. Yeah? So there's a lot of there are a lot of things going on. I use here just as a rule of thumb the 90% quantile of my data. And then I grab out all of my losses I simulated from the Pareto that exceed that threshold. But very careful here, this is what students typically do wrong. They typically stop at this point. They look at the exceedances. So they look at those losses that exceed the threshold. But of course, those losses come from a certain conditional distribution from the original conditional distribution that you exceed the threshold. But then, of course, that's still related to the original distribution you start from. Yeah? Simply take the threshold to be 0, then those simply come from the original distribution. You have to subtract the threshold. You have to look at the excesses. So be very careful in the language here. Exceedances are those losses, the whole distance, so to say, of the whole losses that exceed you, and the excesses are the exceedances subtracted by, you subtract the threshold. So this is important here. Otherwise, I don't end up with the limiting distribution. Good, so I look at the excesses. I try to stay close to the notation on the slide, so it's easier for you to follow. We had Y there, for example. And then I know those should be GPD distributed. Yeah? So I do the same exercise as before, and it's getting a bit more complicated here to look at the histogram, but still this is your histogram, the overlay density estimate, and the limiting GPD density. It's not a very good plot. What you could do is essentially a histogram is a poor man's approximation to a density estimate anyways. If you omit the histogram, you can do a little bit of log-log scale here, but then of course actually you would need to discretize a bit more over here to have like a nicer plot towards the small values, but yeah, that's essentially something I hacked together yesterday evening, so just for you to see and play around with it a little bit. Yeah? Yes?
Zoom in, if you go to the preceding slide, do you have an option to zoom in just to the number picture?
You mean this one?
If I change the axis, if I only look at the area between 0 and...
you could do that. Yeah. But I think it also tells, a little bit of the story to see. But yeah, of course, you can simply grab out those that are in between a certain range. Yeah, true. Yes, yeah. And then, of course, you can also look at a QQ plot here versus the GPD distribution. So, yeah. And you see, the beauty here is really essentially, again, looking at graphics, trying to understand and learn about the theory from graphics. And, yeah, you see you can do these big limiting theorems, 4 big limiting theorems in probability, just by playing a little bit around in R. So that's overall very nice. Good, there are 2 minutes left. The question is, what can we do in 2 minutes? Let me just quickly walk through reproducing some of the plots Paul showed you concerning the Danish fire insurance data set. So here you see the data you've seen on the slides. You can use the mean excess plot, so the sample mean excess function essentially to determine that threshold. And for the theoretical limiting GPD distribution, that plot should become linear ideally at some point. And 2 possible thresholds to look at here are between 10 and 20. So you can argue here's a little bit of a kink, but then afterwards, either from here or essentially from here, it mostly looks linear. And I think the biggest message to give in the remaining 1 minute is that stressing again what Paul said, you really need to do the exercise for several thresholds. never stop at one threshold. Yeah? So you want to make sure your estimates of Xi, for example, are completely stable in the threshold choice, completely robust and misspecify the threshold if you like. Yeah, so you have to redo that exercise. We also did that, especially for operational risk. We looked at a whole bunch of different thresholds. And that's the plot of the empirical excess distribution function and versus the theoretical one. The theoretical one obviously is your GPD limiting distribution. There's still much more to come in QRM tools about that. In EVT, we didn't catch up too much by now, but yeah, so those are the types of plots you get at the moment. And here you see it a bit better than on the slides before. So this is the plot where you have the risk measure estimate here, in this case. Here it's the expected shortfall, yes, at the 99% confidence level, and here you get the levels of the confidence interval. So for 95%, you see it's already quite large.
It's good to know that this curve, first of all, it's even log scale. The log scale it's really very skewed to the right, and this is an important message of extreme value here, because if you really base everything on Gaussian thinking, sort of the standard plus minus 2 times standard errors, symmetric. Of course, extremes is highly unsymmetric. It's skewed to the extreme. So this very clearly shows in this picture. If you go down to the 99% confidence interval around this estimate, this beautiful data is as high idea I've ever seen in my life. You cannot ask for this. At least with a high enough confidence. And that's a fact. In extreme value theory, I remember, sorry, I quickly said that extreme value, in the beginning we were invited by the Federal Reserve in Boston to say, well, when these tools were introduced and operational risk was discussed, they said, of course, a 1 in 1,000 year estimate for operational risk, this must be extreme value theory. It's exactly made for that. So they invited us, Valérie Chavez de Moulin from Uni Lausanne and Johanna Neschle-Hovo is now at McGill. We taught the whole week the yellow book, which is very mathematical, at the Federal Reserve in Boston. And in the end of the week, talking with my colleagues of the Federal Reserve, about 15 excellent people from all over the Fed system in the US, it was basically a conclusion that extreme value theory is not going to solve the problem. The data are just not of the quality that you can apply the standard methodology. And I think it was very positive in that point of view that the extreme value theory pointed, like here also, to this is the end of the line of the kind of questions you can answer. I'm not saying that the operational risk is not important, but you should bring in other economic thinking, discussions. I look at the Swiss solvency test. Under the Swiss solvency test, I can look at my colleagues. We don't have a pillar 1 estimate for operational risk. Under Basel II, we had the loss distribution approach with a very explicit value at risk estimate at the 99.9% level. Now money is scaling back. I'm not saying that these methods, and that's also where our research is relevant, I think, should not be used. There's still something like ORSA, the internal risk assessment exercise for company. Of course, there you should use this methodology in learning about your data. Where I have a problem, where we have a problem is how do you map the data experience, operational risk, internal, external, expert opinion, to capital. There's a lot of uncertainty. Whether the standard model is going to solve that the way it's treated now, I'm not at all certain. I'm not totally happy about that, but that's something else. But I think I really want you to walk away with a correct understanding what EVT can do. I hope you've seen that we can really solve interesting type of questions, that the type of questions you ask yourself in the world of extremes, with a little bit of mathematical notation. There's no deep theory here. There's no Ito calculus, whatever here. It's absolutely first-year probability theory, central limit theory stuff. You can use the mathematics to reformulate the questions you ask in a bit of language of extremes, use limiting result, estimate, and start thinking. But don't walk about the estimates and say, well, this point estimate, let's say, of 58, that's it. Forget about all the rest. No. That curve you now see much better is there. And that tells you the statistical uncertainty. And I'm not even entering model uncertainty, because these data are the nicest of the nicest real data. I think we have a...
We are done.
We are done. Break. So, coffee. Okay. So we start again. So I just briefly skipped one little session, because I only discussed in this lecture, this 1.5 hour or even less summary of extremes, more stressing the big guns of the field, Balkema-de Haan, Pickands, Fisher-Tippett and all that, only looking at IID data or discussing. Of course, if you say, well, if now I have dependent data, there is a theory for dependent data. If I've got non-stationary data, you can also do it, and especially peaks over threshold. If you have stationary non-IID data, dynamically like in Alex's case, you can do it. The standard statement I would make, if there's anything of the non-IID part in your data, stationary but not IID, or you have non-stationary data, first filter the data. So fit the non-stationary component, look at the residuals. If there are IID, if you have done a good fit, good filter, then you may want to use EVT at that level and then transport back through your filter. This is exactly what it's done if you look in time series analysis. So now we have the time series setup that Alex was looking at, and now we talk of conditional EVT. So you have now, let's say, I only do this briefly, but just to tell you it works. So it's so we have our Gauge type process, depends of course on the specification of ZT. In general, you can find a kind of recursive equation, well, recursive, but then well, not recursive really, but linking the value at risk in your dynamic. It's a dynamic value at risk now, but linking it to the innovation, which I assume here to be IID. So this is now the gauge filter. So you think that your model is so that once you've had this fit here, this is your gauge fitting, that takes away the non-IID-ness, you look at the residuals. By the way, very often, it's a stylized fact also that very often gauge filtering gives you close to IID, but still leaves extreme values in the tails, the residuals. So gauge is not really able to get the extremes in the tails away. And hence extreme value theory becomes relevant at that level. So what you then do, once you have in your models these recursive equations or these equations, and you can start estimating extreme value theory at that level, estimate your gauge parameters, and then it go. The world expert is Alex. He wrote a very nice paper. Well, Alex and Rudiger, sitting here. Alex and Rudiger wrote a very nice paper on AR1 gauge 1.1, completely working out this procedure. And it really became a very, very well-known paper where they did that. Okay? So here is exactly what I said. Fit the ARMA gauge, if ARMA gauge is the relevant model. Estimate from ARMA gauge these parameters. Fit the GPD to the IID distribution. That's why there's no T here. This IID. Get the estimate for that and transport it back through the equations. This is not always easy to do. I think AR1 gauge 1.1 works. If you go to higher gauge, and correct me if I'm wrong, Alex, it doesn't work that easily. But this is a standard procedure. So pre-filter your data and then do the analysis and try to bring it back to the system. If, of course, you have very, very clear data that comes in clusters, which you can have, then you may want to do cluster analysis, or there are all sorts of techniques to go beyond IID. But that I think I should have mentioned. So now we go to